Hello and welcome to Power System Analysis 2. We are in module 2.4. Previously we have discussed two different methods of solving power system equations. We have seen Gauss-Seidel method and we seen NR method. Now both of these methods are long and or it might take a lot of memories for the computers. Okay, so most of the time that amount of memory is not available, or rather it will take a lot of time to solve. So some other methods should be prepared. Now these methods are not accurate, but it does the job. So these methods are being discussed here. Okay, it is called the decoupled load flow. So this decoupled load flow method is nothing but we have seen that in the power system the real power has a very strong relation with the angle of the voltage, and the reactive power has a strong relation with the magnitude of the voltage. Although the real power does have the relation between the magnitude of the voltage, but that relation is not strong. Similar for the Q and delta relation. Okay, so the Q and delta and P and V relations are ignored. Okay, and if we ignore that, a lot of values, a lot of calculation can be reduced. So what we do, that means we are decoupling P and V and Q and delta. So this is a decoupled, so that we are neglecting the links between P and V and Q and delta. So it is a decoupled load flow method, or DLF. Okay, so we have a decoupled Newton method. So in any conventional Newton method, half of the elements of the Jacobian matrix represent the weak coupling, okay, and they may be ignored. Any such approximation reduces the true quadratic convergence to geometric one, but there are compensating computational benefits. So if we reduce that, okay, there is a approximation is there, but the computation become much more faster. A large number of decoupled algorithms have been developed in the literature. So there is not only a single type of algorithm, but there are many algorithms on this decoupled nature. So we'll discuss the fast decoupled load flow method here. So the decoupled Newton method. So what is the decoupled Newton method? So what we see is that on the right hand side you have the Jacobian matrix that we have seen previously. Okay, here the elements to be neglected are the submatrices N and J. So all the N and J matrices are to be neglected here. Okay, so we have the relation becomes delta P is equal to H. So the matrix of delta P is matrix of H into matrix of delta. Delta Q is a matrix of L multiplied by matrix of delta V by V. So this H L is nothing but the Vi Vj, and C sin delta Ij and B cos delta Ij, where I is not equal to J. So it can be said that the HII, that is the HII, that is for the diagonal case where I equal to J, it is nothing but BII into VI square minus QI and BII VI square plus QI. Okay, so we are neglecting N and L. The basic thing is this: Hij and Lij, that is the off diagonal one, they have a same value. Okay, that is Vij into C sin delta Ij and B cos delta Ij, and this HII and LII are given for this equation. So the main advantage of the decoupled load flow as compared to the NR method, that is, it has a reduced memory requirement in storing the Jacobian. So it is just that the less amount of memory is required, and there is not much of an advantage for the point of view of speed, since the time of iteration of the DLF is almost the same as NR method, and it always takes more number of iteration to converge of the approximation. So decoupled method here, in the decoupled Newton method, the advantage is only a lesser amount of memory. Now we'll look for the fast decoupled load flow. Now the fast decoupled load flow, there is certain approximation again. Okay, now what is the approximation? The cos of the delta is taken as 1, because the delta, we assume that it is very small. The angle between the power between two buses is small, so the cos of delta ij is 1 and sin delta ij is 0. Okay, and Gij, sin delta ij, is very less than Bij. Now this G and B are obtained from, what is G? G is the real part of Y and B is the imaginary part of Y. Okay, G is the conductance and B is called the susceptance. And Qy is very less than Bii Vi square. So when we take these assumptions, we see that both Hij and Lij now becomes equal to Vi and Vj into Bij, and Hii and Lii, the diagonal elements, is nothing but minus Bii Vi square. Okay, now the matrices H and L are square matrices and with the dimension of NPQ plus NPV, okay, and NPQ respectively. So the number of PQ bus, the matrix size is nothing, number of PQ plus PQ bus plus number of PB bus to number of PQ bus. So the equation of delta P and delta Q has been reduced to the equation 6.84 and 6.85. Okay, now what is this delta Bij dash and delta Bij double dash? It is elements of the matrix B. So the elements of the matrix you will come across, it will be a column matrix. So B will be B dash Ij up, and B and the lower element will be V dash Bij double dash. Okay, so these are the elements that will be formed that will form the delta P and delta Q values. Okay, now so there are certain points of the fast decoupled load flow. So further decoupling, once we have already decoupled and then we taken one more assumption. So this decoupling is obtained by omitting the B dash, omitting the B dash representation of those network elements that predominantly affect the reactive power flow, the shunt reactances and transformer of nominal in phase taps. So we omit this B dash for those elements where there is shunt reactance. So this fast decoupled load flow can be further reduced. We can also neglect the B double dash for the phase shifting effect for the phase shifted elements there in the power system. Now if we divide each of these equations 6.84 and 6.85, okay, by Vi, which is 6.85, 6.85 is given here, the previous these two equations, by Vi, and setting Vj equal to 1 pu in the equations. So we divide them and get those elements in per units. So ignoring the series resistance in calculating the elements B dash, which then becomes the DC approximation of the power flow matrix. So in this sense we have a much more simplified equation. So you can see the previous equation of delta P and delta Q now becomes the equation 6.86 and 6.87. So this is the fast decoupled load flow method. Okay, so these are the values that we have got. Okay, So we can see that the delta P and delta Q should be lesser than our target is to find out the value of delta P and delta Q to be less than a given approximated given estimated value, that it should be lesser than this, then only the value will be sufficiently accurate. So this is the fast decoupled load flow chart. So again we see the you can go in the flow chart, we can see that first we have to see the Y bus, and then we assume the bus voltages, and then we form the B dash and B double dash matrices. Okay, and then we calculate the PIs, and then we calculate whether it is a calculate the QIs, and then we have to check whether the QIs, then we check the whether it is a PV bus. If it is a PV bus, we will check for the maximum of the QI, just as for the NR method. But only thing is that here in the Jacobian we are not solving the Jacobian, rather than we are solving the simplified method of calculation of P and Q. So which is these given by the equation A 6.86 and 6.87. Okay, so this is the end of this lecture. Thank you.